Okay, apologies for the delay, but this deep network unfortunately didn't work. So, but one of the most amazing aspects of the ideas revolving around replica symmetry breaking is their great versatility. In this conference, we already heard talks about subjects as diverse as computational complexity, mathematical physics, neural networks, and signal processing like compressed sensing, and no doubt there's more to come. What I want to speak about is an application of these ideas to a classical problem in mathematics, or specifically combinatorics, namely finding the rank of a random matrix. Specifically, I'm going to be interested in sparse random matrices, so this talk is about something that you might call a diluted spin glass model. More precisely, what I'm interested in is this random matrix model. It's simpler than it might look at first glance. What we do is we create a random matrix like this by first setting up a factor graph like Marc Mézard described in his talk, like that. And this factor graph is a random object. Specifically, we have two types of nodes, these variable nodes here at the bottom and these check nodes here at the top. The check nodes will eventually correspond to the rows of the matrix and the variable nodes to the columns. We fix two probability distributions D and K. D is going to be the distribution of the degrees of the variable nodes. K is going to be the distribution of the degrees of the check nodes. And to be precise, what we do is for each of the variable nodes down here, we choose a degree from an independent copy of this random variable D. And for each of the check nodes, we choose a degree from an independent copy of this other random variable K here. Of course, we condition on the event that the total degree sums match, and then we generate a random bipartite graph with these given degree distributions. So the second moments of these random variables D and K are finite, which implies that the graph that we are looking at is sparse. It's a sparse random bipartite graph with check nodes and variable nodes. Check nodes, like I said, corresponding to the rows of the matrix, and variable nodes corresponding to the columns. And the edges of this graph indicate the positions of the non-zero entries of the random matrix that we are going to create. To generate the entries themselves, we fix any field F, a finite or infinite field, something as simple as F2 or something as complicated as a function field over the complex numbers. And we draw entries corresponding to the edges of this graph from an arbitrary probability distribution chi on the non-zero elements of F. So again, we have the sparse random graph. The edges yield the position of the non-zero entries, which themselves are chosen independently from some distribution on the field F. Is anyone unhappy with the model? Is anyone happy with the model? Okay, most people seem to be quite happy. That's good. So, and my aim is going to be to find the rank of this random matrix. If you substitute a finite field, if you take a finite field, then this corresponds in coding theory terms to finding the rate of a low density parity check code. Now, this problem has received quite a bit of attention. So the first major breakthrough was made in a paper by Dubois and Mandler in 2003, who looked at this problem in the special case that there's precisely 3 non-zero entries in each row. In fact, these entries are 1 because they looked at the field F2. And the number of non-zero entries per column is a Poisson distribution. In computer science, this would be known as the Freak-Sorsat problem. And now you can imagine, so long as you have very few rows, so long as your matrix is very, very flat, very thin, as it were, the rows are going to be linearly independent, so the matrix is going to have full rank. The rank is going to be the number of rows. But then, as you add more and more rows to your matrix, Eventually, that will change, and these guys computed using the second moment method the precise threshold up to which the matrix has full rank. This result was later generalized to a slightly more complicated model where you don't have 3 entries per row but an arbitrary number k of entries per row, but the column degree distribution remained Poisson. And so this original paper was quite nice and short. This paper here already has 30-some pages and is partly computer assisted. And it turned out, and then Cooper, Fries, and Pecton last year computed the rank of this random matrix once you go above the full rank threshold. So up to a certain point, this matrix has full rank, but then it has some other rank, and this rank was computed by Cooper, Fries, and Pecton. And actually, it turned out that these proofs here were specific to the field F2, even generalizing this approach from Dubois and Mandler to the field F3 was far from straightforward. And so this was a contribution by Folke and Gerd, which already ran into 80 pages and was heavily computer assisted based on the second moment method. We later found a different argument which works for any finite field and again for this Poisson constant type of degree distribution. And I should mention finally that there's also been quite a bit of work on this rank problem in denser random matrices. Anyhow, what I want to do is I want to solve this problem for any field and for any degree distributions, D and K. A first step that we can make, a first observation that we can make is we can get an easy upper bound on the rank. How does this work? Well, we can use the following simple combinatorial insight. If your matrix or if your factor graph contains a variable node that only appears in one single check node, that means there's a column that has a non-zero entry only in precisely one row, then you can remove that column and the row, and you are going to decrease the rank by precisely 1. And having done that, you can iterate this procedure in order to, until it converges, until there's no single variable of degree 1 anymore. And at that point, you reach the 2 core of the matrix or of the factor graph. And now you can kind of pose the hypothesis that the 2 core is full rank, that the rank of the 2 core is equal to the min of the number of rows and the number of columns. And now if you substitute the rows back that you removed, you obtain a bound, namely this bound here. Because we can trace this process very accurately on a random graph, we can express the size of the 2 core and the number of things that you removed and so on and so forth very accurately, actually precisely, in terms of the probability generating functions of your degree distributions. This leads to this function phi, and in order to get the 2 core, you ought to evaluate this function phi at 0 and at the rightmost stationary point rho. And the upper bound that you get by studying this peeling process is precisely that the rank is upper bounded by 1 minus the max of this function phi at 0 and this magical stationary point rho. Okay, so that's a simple combinatorial idea, and this idea has been conjectured on the basis of some computer simulations and some belief propagation computations to always be tied by Alamino and Sart in 2008. So specifically what they conjectured was that for any finite field and for any D and K, the rank is always given by exactly the 2 core bound that I just explained. Actually, the same statement was also posed as an exercise in the book by Mizar and Montanari. And apparently, somebody couldn't quite solve the exercise, namely Marc Lelarge proved another upper bound on the rank. So remember, in the 2 core bound, we had here the max of phi of 0 and rho, where rho was the rightmost stationary point. And what Marc proved was that actually you might as well take the max on all of the numbers alpha between 0 and 1. So for the conjecture to be correct, it had better be the case that no matter how you choose d and k, this max is always attained at either 0 or rho. And actually, this proof is not difficult once you know the result on the matching number of random graphs by Bordenave, Lelarge, and Sales from the same year. Okay, so now, is the max always attained at 0 or rho? Well, unfortunately, no. Marc Lelarge himself found a counterexample. Here's another one. So, for example, you could make all of the row degrees equal to 3. So every row contains precisely 3 non-zero entries. And for the column degrees, you could take this probability distribution here. So the degrees are either 2 in 80% of the cases, or in 88% of the cases, or 3 or 11 in the remaining 12% of cases. And turns out that in this case, in some sense, the 2-core is unstable. And for example, removing a single check would unravel the 2-core. As a result, the value rho would be equal to 1 and corresponds to a local min. So the global max of the function wouldn't be at the rightmost stationary point. Okay, be that as it may, Marc Lelarge was brave enough to conjecture that his upper bound is always tight. So that, in other words, you should always take the global max of this function phi. And in some sense, this belief propagation-inspired conjecture is not far from the mark, I would say, because this function phi in belief propagation lingo can be expressed as the beta free energy, let's say in the case of a finite field. And so, in some sense, the correct conjecture seems to be that you ought to maximize this function globally rather than look for some sort of a local stationary point. So in some sense, I would say the physics conjecture is correct in spirit, but missed the possibility that there might be global maxima that are not on the rightmost possible position. Okay, and well, what can I tell you? Marc is in luck. So he actually posed this conjecture only for the field F2, if I'm not mistaken, but actually what we prove is that this conjecture, this formula for the rank, holds for any field F, for any distribution of the non-zero entries, and for any degree distributions D and K that satisfy a this mild moment condition. Okay, so in particular, it also works for fields like the real or the complex numbers, or more complicated fields, like I said, some sort of a function field maybe, or whatever. We don't care what the non-zero entries are. In some sense, what this result hints at is that there's a simple phenomenon that explains the rank formula, and that's in fact what I would like to explain. Okay, so what we are going to do is we are just going to kind of rigorously perform the cavity computation that by now we probably would all really like to do, at least heuristically. So we are going to turn this heuristic idea into a mathematical proof. And the idea was already explained earlier by Marc in his talk. Namely, what we are going to do is, given Marc Lelarge's result, we just need a lower bound on the rank. In other words, we just need an upper bound on the nullity, because as you know, nullity plus rank is equal to number of columns. So all we have to do is we have to prove, we have to show that the nullity is upper bounded by the max over alpha of this function phi of alpha. And to that end, we are going to use this trick that Marc explained, namely, we are going to look at the change in nullity if you go from a random matrix with n columns to a random matrix with n plus 1 columns. So that's exactly the trick that he explained. You go from a system with n variables to a system with n plus 1 variables. And indeed, what we are going to do is we are going to find a coupling between these two random matrices so that you obtain the former from the latter by simply adding a bit of stuff. Unfortunately, it's not quite as easy because depending on these degree distributions D and K, the combinatorial structure of these matrices could be pretty rigid. So as a first step, what we are going to do is we are going to make ourselves a bit of room, provide a bit of wiggling space by introducing a slightly percolated random matrix model, this A and epsilon model, where basically what we do is we remove every row of the original random matrix or every check node of the original random factor graph with probability epsilon independently. As a result, some of the variable nodes are now going to undershoot their desired degree. Originally, I chose degrees for the variable nodes and degrees for the check nodes. Now, I somehow got rid of some of the check nodes randomly. So now some of the variable nodes will suddenly have a degree smaller than the degree they would like to have eventually, smaller than their target degree. And I'm going to call these variables cavities. And these variables that undershoot their target degree are going to be the points where we can manipulate the matrix a little bit. Okay, so having done that, what I'm going to do is I'm now going to take a matrix A prime basically generated by the experiment that I described on the last slide by just removing every row with probability epsilon. In addition, I'm going to remove another bounded number of random rows. So my matrix A prime is obtained from a random matrix as in the original experiment by deleting a bit of stuff. And from this matrix A prime, I'm now going to obtain A n plus 1, A epsilon n plus 1, the matrix of size n plus 1, by adding one more variable along with a bounded number of adjacent linear equations that then connect to a bunch of random cavities of A prime. So that's going to give me A epsilon n plus 1, the matrix of size n plus 1. And on the other hand, I'm going to obtain from A prime by adding a bunch of random equations, again, that hatch onto randomly chosen cavities from A prime, the matrix A epsilon n. So this means that at the end of the day, when all is said and done, what I have to calculate is the change of nullity induced by these two operations. Mind you, this is very much a cavity calculation. For example, if you look at a finite field, let's say the field F2, then the nullity is precisely the log of the size of the kernel, precisely the log of the number of solutions of the linear system AX equals 0. So this is very much something that you would call a free entropy, I expect. So what we are really doing here is we are calculating the change in free entropy upon tinkering a little bit with this random matrix A prime. Now there's an obvious difficulty here, and the obvious difficulty is that we don't a priori know very much about the joint distribution of these points where we attach our new equations and variables. So we have to get a handle on that distribution somehow. And there's a little trick, a little random perturbation to the matrix that makes this easy. To explain this, I have to tell you a little bit about linear relations. So consider any old matrix A, any m by n matrix A. Then I'm going to say that a set of columns is a relation of this matrix if it is possible to generate a linear combination of the rows of the matrix. So you take once the first row, minus twice the second row, minus once the last row, for example. So that you get, by doing that, you get a non-zero vector whose non-zero entries are contained in the set I. In other words, by somehow looking at the rows of the matrix A, you can deduce a non-trivial linear relation amongst the variables in I, in the set I. Okay? Now there's one special case. The special case is that the set I is just a singleton, like here. That by doing a linear combination, you can create a linear relation in the end that only contains a single variable. If you manage to do that, then you know for certain that no matter what you do, this matrix, this variable, for example here variable x2, is always going to take the value 0 in every vector in the kernel. Because you managed to get this linear relation xi equals 0 by doing a linear combination of the previously existing ones. And therefore, I'm going to call these variables frozen, the variables that you can isolate in this manner. And finally, I'm going to say that my matrix is delta L free if the number of non-trivial relations of size L that do not contain anything frozen, any of these frozen variables, is negligible. So free means there's few linear relations of small size that do not already contain a frozen variable. Okay? And that's what I would really like to accomplish. If my matrix were free, then I could look back at this coupling scheme here, and I could say, well, you know what? If I look at the vector induced on these bunch of variables here, well, they are linearly independent. There's no interesting linear relations between them. So I can easily analyze what happens when I attach a little bit of a structure there. So I would really like my matrix to be free, to be delta L free for a small delta and a large L. And so if I could do that somehow, then the only kind of linear dependencies I have to worry about would be frozen variables, variables like this that always deterministically must take the value 0. And well, here's sort of the magical key lemma that makes it all work. It's inspired by the pinning lemma from a previous paper with Will Perkins, Florent, and Lenka, and also by previous work by Andrea. And so what it is the following. It tells you that you can always apply to any matrix a small random perturbation so that your matrix becomes free, so that you basically rid your matrix of any non-trivial short linear relations. Namely, what you do is you simply attach at the bottom a bounded number of rows that each have precisely one non-zero entry in a random position. So the function of these rows is simply to deterministically pin a randomly chosen variable to 0. So you just say, well, you just take your old matrix and then you just at the bottom insist, well, I want x17 to be 0, I want x29 to be 0, I want x5 to be 0. A small number, a bounded number of randomly chosen variables you fix to 0. And it turns out that this small random perturbation brings about this absence of short linear relations that then make the proof work. Indeed, what we do here is, in order to just analyze what happens when you add a new equation, what we do is we simply observe that if these free variables here were frozen to 0 anyhow, then quite clearly adding this new linear equation has no impact whatsoever on the nullity of your matrix. You get this equation for free. If, on the other hand, at least one of these variables is unfrozen, then, well, given that it's extremely unlikely that they form a non-trivial linear relation, then you decrease the nullity of your matrix by 1 by adding this new linear relation to your matrix. And therefore, the expected change in nullity is alpha to the power of degree of this new equation minus 1. So that's the case that they are all frozen, and that's the case that they are not. And in a similar manner, you can analyze what happens when you add this more complicated structure. You get a slightly more complicated formula. Anyway, if you take the expectation of the difference of these two formulas, you get the function phi. And what this shows is that your expected change in nullity is upper bounded by the function value phi evaluated at this value alpha, which is the fraction of frozen cavities. Unfortunately, we have no idea what alpha is. However, we can simply just upper bound the upper bound, namely phi of alpha, by the global max of the function phi. So that's what we do, and we are in luck because what we get out matches Mark's lower bound, Mark's upper bound on the rank. Okay, so that's how the proof works. It's not, well, it's not too technical, right? It's certainly much easier to digest than your average second moment calculation. And it kind of, so in the case of an infinite field, in fact, I wouldn't even know how to set up a second moment calculation in the first place because, well, I mean, how do you count the size of the kernel, right? Okay, anyway, that was the coupling argument. Let me finish with two examples. So here's the freak-saucered example. So this is a random matrix where in each row you have precisely 3 non-zero entries, and in each column you have Poisson D non-zero entries. And this x-axis here obviously is D, and the y-axis is the maximum 1 minus the max of phi, so the y-axis is 1 over n rank of the random matrix. And what you can see is that there's some kind of a phase transition here where this bend occurs, and that's precisely the freak-saucered threshold computed by Dubois and Mandler. And like I said, this picture, this rank plot is completely independent of the field or of the distribution of the non-zero entries. Now, on the right, you see the function phi. So for small values of d, like, for example, what is this, d equals 1 here, for example, that's the function phi that you get. And you see it's nice and convex and has its global max at alpha equals 0, which is why you get this straight line segment here. As we make d bigger, you see that this function somehow starts to bend a little bit. The global max is still at 0 at d equals 2, for example. But as we go on, the function actually develops a second local max at some positive value, which equalizes with the local max at alpha equals 0 at precisely the freak-saucered threshold and takes over once you move beyond. So what this means is that the critical value of alpha shifts from 0 to this magical number here, which is actually precisely the one that would be predicted by the 1RSB cavity method, and then stays there. Here's another example. This is actually more like the simplest random matrix you can think of, presumably, at least the simplest sparse random matrix. Namely, what you do here is you just take an n by n matrix and distribute Poisson D entries that are non-zero randomly in your matrix. And so that's the rank plot that comes out. This axis here is again D, that's the rank divided by n. And again, there's a phase transition there at d equals e, so let's see how that happens. This is the function phi for small values of d, d equals 0.9. In this case, you see it's nice and convex, and its unique global max is some number between 0 and 1. As we increase d, what happens is that this global max tilts a bit to the right. At d equals 2, it's already reasonably close to 1. And then interestingly, perhaps unexpectedly, at d equals e, what happens is that at the global max, the second derivative vanishes and the function flattens. And then, believe it or not, 2 local maxima of the same, exactly the same height appear and start to drift apart from each other. So, in other words, this example would be perennially critical once you move d beyond the value of e. So apparently, we still have to work this out mathematically, but apparently you would get two pure states. For example, if you have a finite field, you would get two pure states in your Boltzmann distribution, presumably with random weights attached to them. Thank you. Probably, yes. I mean, it's yes, yes. I mean, that's it certainly is connected. It certainly is connected. It's a bit more general, I reckon, because this happens for any such matrix problem, and it probably inherits this criticality from that problem. Yes. Yes.
Thank you again.
Thanks.